Session 4.2, measuring strength of association with correlation. So for these sessions, we want to find and interpret the correlation coefficient. What is the correlation coefficient? Let's look at about it. Correlation coefficient, we're gonna use the notation the R. A number R that measures the strength of a linear relationship. Remember the session 4.1? We keep talking about they do have the weak association or strong association. But when we talk about the strong or weak association, we just visualize the scatter plot. We want to use a number to measure how strong or how weak of a linear relationship. And the correlation coefficient R, this is help us to determine how strong or how weak of the association in the scatter plot. So the R, correlation coefficient, is always in between -1 to 1. Okay, R is always in between this number from -1 to 1 here. If you find out the R equal to positive number between 0 and 1, we're gonna say there is positive correlation. It means the graph is going uphill. But if you find your R is in between from -1 to 0, we say this is going to be negative correlation. It means the scatter plot is going to be going downhill here. Okay. The R values close to 0 indicates a weak association. So when your R equal to 0, that means there is a non-linear relationship between these two variables. Okay, hey, keep in mind that session 4.1, 4.2, we are focusing on the linear relationship. The R is also only measure the strength of a linear relationship. So when you find the R equals 0, you only can say there is no linear correlation. Okay, make sure you do have the linear. Because sometimes when you find R equal to 0, there is no linear correlation, but they may have some kind of a patterns. They do have some kinds of correlation. It's just not the linear one. So when the R values close to -1 or +1, indicates a strong linear association. So when the R close to -1, close to here, or close to the +1, it indicates a strong linear association. When R equal to 1, we call this is perfect positive linear correlation. That means all the data is going to be on the straight line. So that's called perfect positive linear correlation. And you will find R equal to 1. Same idea for this guy. When R equal to -1, this is called perfect negative linear correlation. Again, all the points is going to be on the straight line. It's going to be going downhill. So one more time, when your R close to the +1 here, this is represents strong positive linear correlation. Like here, close to the -1, we see this is a strong negative linear correlation. However, if your R is going to be close to 0, we will say this is weak linear correlation. Okay, it means not all the points close to the straight line there. Okay, look at this example. This is an example when you use the data to find the R, you're gonna get R equal to +1. Remember, this is called the perfect positive linear correlation. Because when I draw the straight line here, all the data points is gonna be on the linear equation. This one. When I draw the straight line here, all the points is gonna be on the straight line. So since they're going like downhill, this is a decreasing, so we have a -1. So this is a perfect negative linear correlation. Okay, look at this free example. You can see when R equal to 0.72, 0.72 is really close to the positive one. So when I draw the straight line here, most of the data is going to be around the straight line. Okay, like this one, R equal to 0.48. 0.48, you could think about it, it's going to be close to 0. So I could still draw the line here. I still see kind of the pattern here. But not all the points is around the straight line. So we can say this is kind of the weak linear correlation. Okay, this one, R equal to 0.19 is really close to 0. For this one, I would say that's a really weak linear correlation. Computing the correlation coefficient. Data are converted to the z-score, which are multiplied together. These products are then added, and the resulting sum is divided by n minus 1. In the practice, correlation coefficient is found using technology. If you guys interested how to use the formula to find the correlation coefficient, they do have 3 different methods. That is really complicated. And this is the part like you could read from your book. Use the formula to find out the R in here. Okay, so this is the instruction how to use the TI-84 calculator to find out what is your R. Okay, let's try to do the example together using your calculator. Okay, first, we're gonna click on the stat, click on number 1 added. So let me clean up the data. Remember how to do it? Highlight the L1, click clear, and then enter. Now I'm gonna input the height for the L1 and then the weight on the L2. Okay, make sure this is the pair of the data. It just represent your X and then the Y. Okay, so they should have a equal amount of the data in here. Okay, once you're done, click on the stat, go to the test, and then I'm gonna go up. You're gonna find the linear regression t-test. Okay, linear regression t-test, enter. So my X data is gonna be on L1, Y data is gonna be on L2. Frequency, I only have one set of the data here. And from now, you want to choose not equal to 0. Okay, this is related to the hypothesis testing. We're gonna cover it on the later chapters. So right now, it just remember you're gonna choose not equal to 0. And then regression equation, we're gonna talk about this part on the next session. So just go to calculate, enter. So you will see, go down. You will see the R in here. R is equal to 0.8809. If I want to free decimal space, there will be 0.881 here. Okay, 0.881. This is how you guys finding the R. And since R is really close to 1, we would say there is a strong linear association between the height and the weight. Okay, I need you guys know how to find the R, how to draw the conclusion based on your R in here. Okay, not done yet. We just know how to find the R. And then I want you guys know how to construct the scatter plot using your calculator. So you're gonna click on second step plot, turn on the plot 1 here. And then I'm gonna choose the first icon. Okay, this is gonna be your scatter plot. My data X on L1, my data on Y is gonna be on L2. This is just the mark for the coordinate here. Okay, click on the zoom, go to zoom stat number 9. And then you're gonna see this data here. Okay, this one you could click on the chase. The first data will be 61 and 104. 61 and 104. Go to the right. Second data, 62 and 110. Okay, this is how you guys check one by one in here. So you could see from the scatter plot, the trend is going to be positive going up here. If I draw the straight line here, most of the data is going to be around the straight line. So we believe there is a strong linear correlation. It matched from our R here, right? R close to 1. That means we do have a strong linear correlation. Okay? Okay, I want you guys try this example. Okay, input to your calculator, find out what is your R, 1 to 3 decimal space. And then answer the question, is the linear correlation positive or negative, weak or strong? Okay, check your work. You're gonna find your R equal to 0.906. Okay, so this is really close to 1. And then for the R, this is a positive. So even though I don't look at the scatter plot, I could tell this is gonna be positive and strong linear correlation. Okay, it's better you could use your calculator to look at the scatter plot and then track your work. Okay, notes about the correlation coefficient. First, if all values of either variable are converted to a difference scale, the value of R does not change. So when you use the rectangular coordinate system, you could change like the difference scale. The R does not change. And then the value of R is not affected by the choice of X and Y. Interchange all X and Y and the value of R will not change. So this is really interesting. Like we do have the weight and the height, right? If we switch it, use the weight has the X, use the height has the Y value. When you use your calculator to calculate the R one more time, the R will not change. Okay? R is unitless. We don't have any unit for the R. And R is very sensitive to outliers, which can dramatically affect the value of R. For this part, you may want to be careful. So every time when we do the example, just the previous one, before we finding the R and draw the conclusion, you want to construct the scatter plot first. Make sure if there's an outlier. Okay, if there's an outlier, it may be affect the association because the outlier make the R really small, and then you may draw the conclusion say this is a weak association. Okay, so it's better every time you're gonna construct the scatter plot. Look at it if there's outlier. If they do have the outliers, you may want to remove the outliers and calculate the R. And then you're gonna draw the conclusion. R is only useful to measure a linear trend. Always graph your data first before computing R to make sure the association is linear. Okay, this is a really good point. And also, when we keep talking about the R, this is measure the linear trend. Remember, we keep saying the linear correlation. Okay, you may find the R is really weak, and you could draw the conclusion there's a no linear correlation, but it's better you want to look at the scatter plot. They may have some other pattern, they may have some other correlation, it's just not the linear one.